So start recording and then share the content, stream, start podcast, and then okay. Hmm, okay, now, so today is May 8, 2021. All right. So today we're going to start chapter 7 from Kessler Barker. There is a small topic left called complete statistics that I will from the chapter 6 that I will do when I will do the I will request to prove some properties like minimum variance unbiased estimator. That time I will just cover it. But major concepts of chapter 6 that I have covered. So chapter 7 from Kessler and Berger is on point estimation. All right. Okay. So there are typically point estimation. The concept of point estimation is if you have a parameter of interest theta, you want to estimate that parameter and you have a statistic t. So suppose x tilde is your data, typically x1 to xn, n sample of size n, coming from some parameter distribution with some parameter theta, and your theta is unknown, and x tilde belongs to chi. Typically, it is real line on some values of real line. If it is discrete, it would be integers or something, but typically it's a real line. Now, t equal to t of x tilde is called estimator, will be some function of pure function of data, estimator of theta, and typically t of small x tilde of t is called estimate of theta. So basically, based on the realized value, if you apply the function t or whatever the operation, t could be a function, it operation, whatever you call it, which will be pure data driven process and which will effectively estimate the theta. So one is estimator of theta. When you are writing it as a function of random variable, then we will call it estimator of theta. But if you are writing it in function of realized values of random variable, then we will call it estimate of theta. Now, essentially in this chapter, we will focus on two things. One is how to find an estimator, how to find an estimator. That's typically, I think that is the section 7.2, typically called method of finding estimators. That is section 7.2. And we will try to answer the second question. The second question is it's what are the properties of estimator or method of evaluating estimators? How good the estimators are. Estimators. That is section 7.3. Okay, typically 7.3 is, it says method of evaluating estimator. Basically, we are in this section 7.3, we are saying that how good the estimator is. If you have two estimator, first of all, the process, first of all, you have in the section 2, section 7.2, we will figure out how to figure out an estimator. Now, there are 2-3 different way to figure out an estimator, and you can come up with two different estimator. If you have a estimator 1, T1 and T2, which one is good? Which one is good? So this is or which estimator you'd like to use. So first, today mostly we will focus on finding estimator. Okay, so the first one is method of finding estimator. Method of finding estimators. Okay. In this, in the book, there are 4 methods. In Kasselberger, there are 4 methods are given. First is method of moments, method of moments. This is the oldest method that was developed by Carl Pearson in 1902. So more than 100 years, 120 years old method. Then is maximum likelihood estimator, Emily. This is almost also 100 years old concept, around 19, I think, by Fisher, R.A. Fisher, around, if I'm not majorly mistaken, around 1925 or 1930. One of the paper, I have to check the history. I think around that time he figured out. C is Bayesian estimator. Now this is a interesting thing. So Bayes' paper came in front is almost 200 years back. So Bayes' theorem is 200, 300 years old. So Bayes' estimator is, but for many reasons, it went into the back burner. But recently, I think when with the advent of computer and personal computer, PC, now I think Bayes estimator, Bayes method becomes more popular. And the fourth method is EM algorithm. So EM algorithm. Now, if you look into the most popular method, then I have to say this is the most popular method across machine learning, statistics, math, physics. That is something people use oftentimes without knowing the importance of the method and all these things. Okay. And then probably the second most popular method is Bayesian estimator. And they actually have a lot of connection. And I will try to reveal some of the connections. Now, this is method of moment turns out to have only a very restricted application. Only restricted application with some toy problems. EM algorithm turns out to be very problem specific. For certain problem, it has a very nice solution, but there are many other models for which finding EM, estimator using EM algorithm turns out to be a bit challenging. So I'm not sure if I will cover the EM algorithm, but definitely the first three I will cover. The first one is method of moments. I believe Professor Ramurthy earlier has covered method of moments and likelihood, right?
Yes, sir.
Yeah. So I'll not spend much time, but I'll just talk about the method and then I will move on to the likelihood. I think he covered first two, right? Or did he touch the third one, third or fourth?
No,
He
sir,
only
just
did the
first.
First two.
Yeah.
Likelihood, did he cover likelihood?
Yes, sir.
Okay, so the first two he did, and the second and third he did not. So I'll do the first three. Then depending on the availability of the time and all, I'll do the EM algorithm. So the first thing is method of moments. I'll quickly do that. So the x1, x2, xn are some IID random variables. And with some f theta x, where f is probability function. When I'm saying probability function, it could be probability mass function or density function, depending on if x is continuous or discrete. Okay, so I'm just saying it is a probability function, and theta is the target parameter. Is the target parameter. So what it does is it calculates the sample moments and population moments. What is a sample moment? Sample moment is say m1 1 by n summation I equal to 1 to n xi, and then mu 1 dash, this is expected value of x, which is integration over time x fx dx. Then m2, the second raw moment, is 1 by n summation xi square, which is mu 2 dash expected value of x square, fx dx. Then in this way you go up to whatever moment you need, you go up to this. Mu k dash expected value of x to the power k integration x to the power k fx dx. Okay, now what it does, it said, okay, we will approximate the mu1 dash with m1 dash, we will approximate the mu2 dash with m2 dash, and we will approximate the muk dash and mk dash. That's very simple. I mean, you can just write a simple function in R or Python which will give you all the moments that you need. That's, life is simple. And then what you do, basically you express your theta as a some function of the mu1 dash, mu2 dash, dot dot dot, mu k dash. So basically whatever your theta, you try to express the theta as a function of the moments of the distribution. And then your method of moment estimator is theta hat is h of m1 dash, m2 dash, mk dash. Okay, so this is the idea, that pretty much. So theta hat is moment estimator. Okay, so this is pretty much the idea. So one simple example is, let's take the normal distribution case. Let's take an example of normal distribution. So x1 to xn, follow IID, normal, mu, sigma square, and then we do know that expected value of x is mu itself, and variance of x is sigma square. Now what is variance of x? Variance of x is expected value of x square minus expected value of x whole square. So we can call it, this is mu1 dash, and this is mu2 dash minus mu1 dash square. So what will be my estimator? My estimator will be, for mu, my estimator will be mu hat, which is m1 dash, and for sigma hat square, it will be simply m2 dash minus m1 dash square. So basically what I just did here is I express the target parameter sigma square in terms of moments, in terms of simple moments. And then you just plug in these things. And not now for normal distribution turns out to be very simple. Even for standard binomial, Poisson, gamma, these are very simple examples. But beyond simple examples, it's very, very difficult actually to go beyond univariate distributions. Okay. All right. Next, anybody have any question? I think it's very simple, concept-wise very simple. Okay, next is method of moment is done. Next is maximum likelihood estimators. Maximum likelihood estimator. Now, remember that this maximum likelihood estimator is something even you will see that even deep learning neural network models, when in your third semester, when Professor Madhavan will teach you advanced machine learning course, he will introduce the deep learning neural network models. Even the parameters of the deep learning neural network models are generally estimated by maximum likelihood estimator, maximum likelihood method, with certain version, or which we call in classical statistics penalized maximum likelihood method. Turns out that those do have some certain connection with Bayesian estimation method. So I will try to explain it over the next 2-3 lectures between the connections between likelihood estimation method and the Bayesian method. But we have to be very slow. We have to move very slow. So you have to be a bit patient here. So the likelihood function typically defined as, I think we already defined in our last 2-3 classes, but I'm just quickly writing it down. Likelihood defined as typically L theta equal to product L. Now I'm just considering theta is here, could be k many parameters given you have x1 to xn n samples. Okay, so I'm doing it on, so theta could be k variate distribution also, theta 1 to theta k, not necessarily univariate. So theta belongs to k dimensional parameter space. So x1 and to xn is the data set. So that typically we call it, we define it as a equal to 1 to n f of small xi given theta 1, theta 2, theta k. So I'm defining my likelihood as a function for k parameter distributions. In your model, you can have k parameters which you want to estimate. So I'm defining as generic as possible. Okay, not necessarily single parameter. Now, what is maximum likelihood estimator? So if this is your likelihood function, if you're in one dimension, if this is your likelihood in your theta is here, yeah, your likelihood function is here, you naturally here where your likelihood is maximum, you project it here. So this is the parameter is which you like to estimate as your MLE. As your MLE. Theta hat is your MLE. So this is the idea. So that means theta hat is my MLE, where the argument of maximization problem over L theta given X tilde. So it's a maximization problem. Remember that. Or this is same as argument of maximization problem of log of likelihood, because log is a simple one-to-one function. So I want to work with, instead of likelihood, I want to work with log of likelihood. Can anybody tell me why I want to work with log of likelihood? We discussed it earlier, but still, if you can't, if you forget, in case you forget. So, do you remember?
Sir, it converts the product into sum.
It's convert the product into sum. That is true.
And it is monotonic, like preserves
Yeah.
the property of L.
Correct. Correct. One more problem it avoids, which is actually very important from numerical point of view. Remember that your F is the density function is typically positive. Now, for it might be greater than 1, but many times the density function, the value it will take will be less than 1. So it will be fraction. And if you take a product of many fractions, it will become very small and smaller and smaller value. And as a result, there will be a time when computer will say that, okay, I can't handle it anymore. I will just now round it off to 0. So that's typically called the floating point error. So in order to avoid that, also can be easily avoided by taking log of the likelihood. It will induce the same problem. Okay. In some of the, so basically it turns out that it's an optimization problem. And some of the, so you can just write down your, you can take your model, you write down your likelihood or log likelihood, put it into a optimization subroutine to optimize over the parameter space theta, and then find the value of theta where this likelihood is maximum, and that's will be your solution. Or what you can do, in some places by default setup is minimization, so you can solve it as a minimization problem as well. By instead of working with log likelihood, you take the negative log likelihood of theta given X. Actually, I should use small x, not the big X. Yeah. So essentially, MLE, finding MLE is an optimization problem. Finding.
But like, why will we minimize the likelihood?
No, this is negative log likelihood.
Okay.
Suppose your optimization routine do the minimization. Okay. So instead of maximizing the log likelihood, you can minimize the negative log likelihood. That will solve the same problem. And hence it will give the same result. And that's why I'm saying equal to. These are all equivalent. Okay. So the finding MLE turns out to be an optimization problem. the and hence in data science, optimization is an important topic. Um, now, what I'll do, I'll try to do it for one example. So if L is differentiable, if it is differentiable in theta I, then what we can do, we can differentiate with respect to theta I and equate to a 0 and solve it. Okay. And of course, we have to check del 2, del theta I2, L theta tilde given x tilde at theta equal to theta hat MLE, which is solution from the first equation, is negative. Sometimes this is also called Hessian or second derivative, whatever part of the Hessian. And it will play a role in some of the inference. I'll gradually come into this. Now we'll take an example and we will use this to prove some of the small example. And of course, for the bigger problems, bigger models, complicated models, we have to solve it numerically. So let us do for some small problems. Example 1. So x1, x2, xn is IID normal theta 1. I'm assuming my variance is completely known, value 1. So it's a one parameter model. So my likelihood is half x I minus theta whole square. So we can write it as 1 by 2 pi to the power n by 2 e to the power minus half summation I equal to 1 to n xi minus theta whole square. Now if I take log of it, log of L theta given x tilde, what I get n by 2 log 2 pi minus half summation equal to 1 to n xi minus theta whole square. Okay, and then I differentiate it with respect to theta. Of course, this is a constant, so nothing to be there. And what we have is effectively minus half 2 summation xi minus theta. So this cancels. If I equate this to 0, then effectively I'm left with summation xi minus theta equal to 0. Equal to 0. So shall we consider, so that means we can say n theta equal to summation xi equal to 1 to n. This is also equal to 1 to n. That implies theta at 1 by n summation xi or x bar or sample average. Therefore, maximum likelihood sample mean is the MLE of population mean for Gaussian distribution. Particularly this type of one, when you know the one, this one. You can do it for the sigma square also, and I'm leaving it for you. I assign that to you. So, okay. So now I am going to prove our theorem, or it's a small proof, but it's a very interesting result. It's a very, very powerful result. This is theorem 7.2.10 from Kasselberger. It's called invariance property of MLEs. Invariance property of MLE. Okay. Now, if theta hat is the MLE of theta, then for any function tau theta, the MLE of tau theta is tau theta hat. Well, that's an interesting result in the sense, if my second example, before I go into the proof and all, I want to discuss the importance of this theorem. Why it is so important? Why it is important? Now imagine you are interested in, suppose x1, x2, xn follow some distribution, say binomial np. Suppose n is known, p is unknown, and p lies between 0 and 1. Okay, what about one can show I'm leaving it as a homework, p equal to summation xi over n is the, or p hat is the MLE of p. Actually, I'm making a mistake here. Let us take even simpler. Let's make it 1. Otherwise, there will be some issues. 1. Bernoulli distribution. Then it will be, yeah. Okay. Now the question is, but we are interested in, suppose xi is, if it is, certain disease or not. Okay. So xi equal to 1 if disease, 0 not. Okay. If this is the case, it happens with probability p and does not happen with 1 minus p. But the doctors are interested in odds of the disease. What is the odds? Odds is defined as p by 1 minus p. Now, what is the MLE of odds? This result tells me the MLE of odds is O hat, which is p hat by 1 minus p hat. Wonderful. I really don't have to figure out what is the likelihood of odds, and then I have to do the optimization, solve the optimization problem to get the odds. All I have to do is that I have to figure out the MLE of the core parameter, and then any functional form of that, maybe that functional form has a particular importance in the science. Here, odds has a particular importance in the science, and suppose the doctor or the particular domain is more interested about this functional form of the parameter rather than any the original, the proportion. Fine, no problem. You just plug it in the MLE. The resulting output is also MLE. That is what this theorem is talking about. That if you have theta hat MLE, if you have a function tau theta, you plug it in, you get it. And I checked it. The one-to-one correspondence is also not necessary. The way it is being proved, that assumption is, so even if it is a not one-to-one, it is still valid. Okay, so that's an interesting theorem, and let me quickly give you the proof is very simple. Let me discuss the proof. Suppose eta hat denotes, eta hat is the value that maximizes the likelihood of eta. Okay, so you have to show, basically what we have to show that L star eta hat given x tilde is same as L star tau of theta hat given x tilde. So where my main target is function is, say, suppose h of theta. This is what I want. Oh, I use tau. All right. I use tau here. I should not use jump of the notation. Okay. So L star eta hat given x tilde, you can basically, this is a supremum of eta where this is supremum over L theta given x, where theta is tau theta equal to eta. So this is what we got, and what it tells us effectively that supremum of theta is L theta given x tilde. Now you can ask me, how can I make this jump from here to here? Can anybody guess? This is effectively L theta hat given x tilde, but this, from this step to this step, how can I do that?
So this is possible if the function is like increasing.
Monotonic, you are saying.
Um, yeah,
Okay.
monotonic, but increasing here because it's supremum.
Actually, there is a result that are being called for here. The result is saying that iterated maximization is equal to the unconditional maximization of over theta. This result is being pulled. It is sort of it's like I have somehow here I have the theta hat, and then I have done some transformation of tau theta. Now that theta hat has now come here, transformed into here, but because of the transformation, this likelihood is also somehow topping here. So this called, so it's like, and that is what it is basically trying to say, that iterated maximization of maximization equal to the unconditional over theta. So, and then effectively it says that L theta hat x is effectively, and this is, you can call it L, and this is actually your L star. But whatever it happens, that here when you are optimizing here, so here also you are getting the same optimization. So even if it is projecting here, after the transformation, the maximization is not changing, and that is what this particular result is talking about. Okay, so that gives us, effectively makes our life simpler. This is a result from optimization effectively. L theta x, and this is same as L star tau theta hat given x. So this is what it's talking about. I think I have given you one example that I'll give you another example. The example is again the same example. So x1, x2, xn is IID Bernoulli 1 comma p, or binomial 1 comma p, 0 less than p less than 1. So x1, x2, xn. Okay, n is the sample size. Now we do know that p hat is our MLE. I'm giving you it as a exercise, you have to show that, assuming this is fine, is the MLE of P. Okay. Now, so expectation of X is P. We do know, and what is the variance of X? P into 1 minus P, which is, now if somebody asks you what is the estimator, maximum likelihood estimator of variance of X. So generally we jump said, okay, what is the estimator of variance of X? So this will be a square 1 by n summation xi minus x bar whole square, correct? That is we jump to say. But now I have an alternative estimator. Now alternative estimator is variance of is p hat into 1, sorry, p hat into 1 minus p hat is my variance of X. This is my maximum likelihood estimator for variance of X, or the binomial proportions, or binomial distribution. So should I use this or should I use this? Which one I use? So now I have two estimator. Either I can use this guy or I can use this guy. Which one I should use? So we will talk about it when we will, and that is where this second part comes, that how to evaluate which estimator is better and which one I should use. Okay, so I'll not, so I think I just try to pose the question, and so anybody have any question so far? I think now up to this, I think fine. Next day we will start the Bayesian estimator, and we will try to do the connection between Bayesian estimator and the likelihood estimator. Okay.
Okay, sir.
All right. Anybody have, if you do not have any question, then we can, today's class. Somebody has written something. Okay. All right. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you.